So good morning to dear students and good morning to all. So today we'll discuss about variable loading in this presentation. So here variable loading is an important in design. So here we cover the basics of fluctuating load and important terms related to variable loading and test types of stress cycles, endurance limit and SN curve, and rotating beam fatigue testing mission for estimating the endurance limit, Soderberg and Goodman equation, fatigue stress concentration factor and loss sensitivity, design of machine elements under the fluctuating stresses or loads. So here we discuss the importance of the variable loading. Then we go to terms. So here in the previous videos, we discussed the static loading. Static loading is nothing but only magnitude is fixed and point of application is fixed and direction is also fixed with respect to time. But this kind of loading we observe only in few machine parts. But the many of the machine parts are subjected to variable loading like axles, shafts, crankshaft, connecting rod, springs, piston, etc. These are the some of the elements subjected to variable loading. Okay. Now we discuss this variable or alternating stresses in this video. Fluctuating stresses. So already we know, we are assumed that the loads acting on the mechanical parts is taken as static. Okay, many applications the components are subjected to forces which are not static but vary in magnitude with respect to time. These stresses induced, such forces are called fluctuating stresses. Then here we observe that 80% of the mechanical parts, 80% of the failures of mechanical components are due to fatigue failure resulting from fluctuating stresses. In practice, the pattern of variation is irregular and unpredictable because in case you drawn the stress time graph like this or stress time graph, the variation of uh, stress is very irregular and unpredictable. Okay, the purpose of design analysis, simple models for stress strain relationships are used. The most popular model for stress strain relationship is sine curve. Now, to analyzing the completely reversed or cyclic stresses, we are taking the rotating beam of circular cross section. So, and varying load W as shown in the figure. This load induces stress in the beam which are cyclic in nature. A little consideration will show that the upper fiber of the beam at point A under compressive stress and the lower fibers are at the tensile stress. So by seeing that we can understand after half revolution a point B occupies a reaches the position A and the point B occupies the position of point B. Thus the point B is now under compressive stress and the point A is under tensile stress. The speed variation of these stresses depends upon the speed of the beam. From the above, we see that for each revolution of the beam, the stresses are reversed from compressive to tensile. The stresses which vary from one value of compression to same value of tension or vice versa are known as the completely reversed or cyclic stresses. So for understanding further, just I am taking one beam and subjected to bending like this. So side view of the circle, side view of the shaft is circle. Here I am taking A1, A2, A3, A4. For analyzing the stress time plot, just we are taking theta is in degrees and stress in the y-axis. First I am taking A1 is the starting point of your rotation of the shaft, that is this point, and 90 degrees of rotation means this curve reaches to this position, and after half of the revolution this point reaches to 180 degrees, and same A1 point is reaches to this A4 point. So that is this value reaches to 270 degrees, and the further A1 reaches to the normal original position, then it reaches to one complete revolution. Like this, the shaft will rotate number of revolutions. But for our analysis, we are taking only small segment. This segment I am considering, and we try to explain the various terms related to the variable loading. So here I am taking stress cycle. Stress cycle is the smallest portion of the stress strain plot. So this is like this. We have number of cycles. In that I am taking only small portion, which is repeated periodically and identically. It is repeating periodically and identically. So first one is in this the maximum stress, because here we have different types of waves will be like this. We are considering only maximum and minimum. So it is the largest algebraic stress in a stress cycle. So in this case, tensile stress is taken as positive and compressive stress is taken as negative. In a similar way, we consider the minimum stress. So this is the smallest algebraic stress in a stress cycle. So in this also, the sign convention is same. Tensile stress is taken as positive and compressive stress is taken as negative. Then we'll see some of the important terms related to this variable loading in order to design the mechanical components. First one is range of component. Range of component is nothing but it is a difference between the major maximum stress and the minimum stress. This is nothing but range. That is sigma max minus sigma min. But in our design calculations, we consider only variable stress. It is also called as the alternating stress. So this is equal to 1/2 of the range of stress. The other important term is the mean stress. Mean stress is the algebraic mean of the maximum and the minimum stress in one stress cycle. Then other one is stress ratio. It is defined as the ratio of minimum stress to the maximum stress. Then other one is amplitude ratio. It is the ratio of variable stress to the mean stress. So these are the terms we may use while designing the mechanical component. Some different types of loads. Here we see completely reversed load. Completely reversed load nothing but the load is varying from plus P to minus P. Means its magnitude is same in case P value is 100. So 100 megapascals or so. And but here plus minus it is direction is changing, but only direction is changing, magnitude is same. That is nothing but completely reversed stress cycle. So this is magnitude is same, only direction is changing. Then other one is alternating load. Here load is varying from plus P by 2 to minus P. In this case, magnitude is changing and the direction is also changing. In the case of fluctuating load, okay, generally values are both plus P by 2 and plus P. Only magnitude is changing, no direction change takes place in this cycle. Other one is repeated load. Here magnitude is varies from 0 to plus P like this. So there is here minimum stress is 0. Okay, so here we studied 4 cycles. Among these, the most dangerous cycle is the completely reverse stress cycle, because minimum stress is 0. It is reverses completely. It contains only the variable stress. Okay, Next, here we see static load and for complete reversal load. In the static load case, sigma max is plus and sigma min is also plus. So in that case, mean stress is sigma and variable stress is 0. So that's why only mean stress or stress is contribute to this static load. In case you are taking the reversal load, this is plus P to minus P. So if we calculate sigma mean, its value is 0 and sigma variable value is sigma. So in the complete reversal loading, mean stress is 0, only variable stress is acting on this part. So here one more thing is fluctuating stresses. In this type of stresses, both mean and variable component of stress exists. So that is nothing but this is the mean and this is the variable stress. Okay? A complete reverse stress is superimposed on the mean stress. So this is. Then other one is the reversed stress cycle. In this reverse stress cycle, mean stress is 0. So mean stress is 0. So the variable stress reverses completely from tension to an equivalent value in compression. Here the value is changing from plus P to minus P. Okay, magnitude remains same. So this is regarding the reversal stress cycle. Then next one is repeated stress. In this stress, the minimum stress is 0. So that stress varies from maximum to 0 in each cycle. Only magnitude is changing from 0 to plus P, not in direction. So that is sigma minimum is 0 in this case. Okay. Then like this. Next, we focus on this endurance limit. Okay. Endurance limit is the property of the material under variable loading. So fatigue limit or endurance limit gives the same meaning. This is defined for the material. So this is defined for, we've seen 4 cycles, stress cycles. Here we are defining the endurance limit for the maximum value of completely reversing stress cycle that the standard specimen can sustain for unlimited number of stress cycles without fatigue failure. So that is nothing but the endurance limit. So fatigue limit or fatigue test cannot be conducted for unlimited or infinite number of stress cycles because we don't know when the component undergo failure. So that's why fatigue test cannot be conducted for unlimited or infinite number of stress cycles. So that's why 10 to the power of 6 cycles is considered as the sufficient number of cycles to define the endurance limit. The endurance is denoted as sigma E. It is the criterion of failure under fluctuating stresses. So from the experience and for practical reasons, the number of cycles may be taken as 10 to the power of 7 or 10 to the power of 6 to define the endurance limit. So this is for only ferrous materials like steel. There is no endurance limit for non-ferrous materials. Okay? This is regarding the... Now, how to calculate this endurance limit? So generally we use rotating beam fatigue testing method to find out the endurance limit. The schematic diagram is drawn like this. And this is the same diagram, but in Bandari textbook I have taken. So here I am taking the standard specimen. Standard specimens having the 875 length, nominal diameter 7.65 and highly polished. Okay. So here this specimen is placed in this arrangement, and here we are arranging the self-aligned ball bearings. This self-aligned ball bearings only allows the radial loads or vertical loads. Now here we see the weights. So by adjusting the weights, we can apply the bending moment to the specimen, because in the rotating beam, in the rotating fatigue testing mission, specimen is subjected to only bending. Now, here we have the electric motor. By using this electric motor, we give the rotation to the specimen, and how many number of revolutions we observe the fatigue crack on this specimen. That information, that is that a number of revolutions are uh, considered on the revolution counter or displayed on the revolution counter. Next, so here the endurance limit is determined by means of rotating beam machine, already we know. So this was proposed by R.R. Morey. So this is having the standard size and highly polished surface finish and rotated by electric motor, and the number of revolutions before the appearance of the first fatigue crack are recorded on a revolution counter. Now we are using self-aligning ball bearings are used to ensure that only radial loads are applied to the specimen. The specimen is subjected to pure bending moment. Magnitude of bending stresses are adjusted by means of these weights, like this. So this is the schematic arrangement. Now how we do the procedure in that. To determine the endurance limit of a material, a large number of tests are carried out. So each test consists of applying a constant bending load, and the number of revolutions or stress cycles before the appearance of first crack are measured. Then we'll start the procedure. First we draw SN curve, S and SN curve. Here first we assuming that the specimen or mechanical component will fail before reaching to the ultimate value when that part is subjected to variable loading. So first point is, during the first test, the bending stress is kept slightly less than the ultimate strength of the material. So first we take ultimate strength of the material. Then we record the number of cycles for getting the failure. Then we conduct the second test, in that the stress is slightly reduced and second test is carried out. This procedure is then continued for large number of tests. Okay. The results of these tests are plotted by means of SN curve. So SN curve is nothing but a graphical representation of a maximum stress versus the number of stress cycles, okay, N before the fatigue failure on a log-log. We are plotting these failure points on the log-log graph. Each test gives one failure point on SN curve. In practice, the points are scattered because points may be scattered like this. Okay, and the average value is drawn through them. So the curve is drawn through the average points. For ferrous materials, the SN curve becomes asymptotic. Asymptotic means this curve is parallel to the X and X axis. So at 10 to the power of 6 cycles, so that is 10 to the power of 6 cycles, which indicate that stress amplitude corresponding to infinite number of stress cycles. The magnitude of this amplitude is at 10 to the power of 6 cycles, represents the endurance limit of a material. So important note is, for steel, a knee formation occurs in the graph. Beyond this knee, the failure will never occur, no matter how great the number of cycles. The endurance strength corresponding to knee is called as the endurance limit. This is the endurance strength corresponding to knee, we call it as the endurance limit. The SN curve shown in figure is valid only for the ferrous materials. Next, we move to for non-ferrous materials like brass, copper alloys, aluminum, magnesium. These are the non-ferrous materials. So for this, the SN curve slopes gradually. even after 10 to the power of 6 cycles. So the curve never becomes horizontal. There is no knee formation occurs. That is nothing but in case you are drawing the curve like this. So you never the becomes asymptotic or parallel. It always descending like this. So these materials do not have the endurance limit, but endurance strength can be established for these materials. So the complete SN curve from 10 to the power of 0 cycles to 10 to the power of 8 cycles is shown in figure. So this. There are two regions. One is the low cycle fatigue and the other one is high cycle fatigue. First one is low cycle fatigue. So any fatigue failure occurs when the number of stress cycles are less than 1000. That is called as low cycle fatigue. For example, we take failure of studs on truck wheels. So in those applications, we observe this low cycle fatigue. Then other one is high cycle fatigue. The fatigue failure when number of stress cycles are more than 1,000, is called as high cycle fatigue. So failure of machine components such as springs, ball bearings, and gears that are subjected to fluctuating stresses. So generally, these mechanical components withstand up to 10 to the power of 6 millions of revolutions or number of revolutions. So I have clearly placed a diagram, low cycle fatigue. So its value is 10 to the power of 3 and high cycle fatigue above 10 to the power of 3 and up to till 10 to the power of 8. So this is then how to design for fatigue loading. Okay, here design of machine member under fatigue loading will depends on the stress cycle. So we've seen already number of cycles. One is the fluctuating stress cycle, a repeated stress cycle, and a complete reversed stress cycle. So based on these cycles, the design procedure will vary. First, we focus on the completely reversed stress cycle. Here the mean stress is 0 and the endurance limit stress is used for determining the failure criteria. Okay. The maximum stress induced in the material will be the variable stress sigma V. Okay. So however, the calculated variable stress should be increased by the fatigue stress concentration factor, since stress concentration is very important in fatigue loading. So already in the completely reverse stress cycle, we seen mean stress is 0, only variable stress is contributed to failure. So for the variable stress, the criterion of failure is endurance limit. So based on this, we write KFC, KFX into CV less than or equal design stress. Here design stress is sigma E by factor of safety. So for shearing stresses, same equation may be written as sigma Vs and sigma Es like this. Now the rest of the cycles, we use the same procedure. Stress cycles other than completely reversed stress cycle. Here both mean stress is not 0. Both variable stress and mean stress contribute to failure. The results of the variable loading made with different and with various combinations of mean and variable stresses are shown in the figure. With the failure points marked thereupon, this sometimes known as Haig-Soderberg diagram. The parabolic failure curve was proposed by Gerber, while the straight line proposed by Goodman. Let us try to understand this. So on x-axis we are taking mean stress, on y-axis we are taking variable stress, and on mean stress the failure conditions are the yield point stress and ultimate point stress. And for variable loading, the criterion of failure is sigma endurance. So by changing the mean and the variable stresses, uh, by changing the mean and variable stresses, so we get the failure points. Okay, so we see this. Sorry for the interruption. So failure data generally falls closer to the parabolic curve. However, due to scatter in the points, the straight line relationship is usually preferred in engineering design. We see note 1. When the variable stress is 0, means this is becomes 0, then the load is purely static and the criterion of failure is either yield point stress or ultimate point. When the mean stress is 0, means it becomes 0 like this, so then stress completely reversing from criterion of failure is the endurance strength. So this is. Then here we focus on the Soderberg equation. Okay. So Soderberg criteria is mainly applicable for ductile materials, since it precludes the possibility of failure by yielding. According to Soderberg criteria, the failure line, this is the failure line. This failure line is taken as straight line joining the endurance limit and yield point strength as shown in figure. This failure line we call it as the Soderberg failure line. So the line AB connects the sigma E and sigma YP as shown in the figure. Is called as Soderberg failure line. If a suitable factor of safety is applied to the endurance limit and the yield strength, this safe line will be drawn like this. Safe line may be drawn parallel to the AB line like this. So in this, let us consider a point P on the line CD. Now from the similar triangles, here I am taking, this is one triangle and this is another triangle. So with the help of this triangle, we try to find out the Soderberg criteria for. So here from this diagram I try to explain. So here I am taking FE. So this is FE and FC. This is the triangle I am taking. Then the other triangle is, so vertical lines I am taking first OB and OA like this. Then EFE by EFC nothing but OC minus OF like this. So the remaining values are same. Remaining values are same. So OB by OA. In this case, FE nothing but sigma V. So this is, and this is sigma V and sigma Y by factor of safety minus sigma M, sigma C, sigma UP. So rearranging this equation, that is sigma Y takes sigma Y common, 1 by factor of safety minus sigma mean by sigma YP by 1 by, so finally we get 1 by factor of safety equal to sigma mean by sigma YP plus sigma V by sigma endurance. So for static stress, the criterion of failure is sigma yield point. For variable stress, the criterion of failure is sigma endurance. So easily you can remember this equation. Static equation and its failure criteria. Variable stress and its failure criteria. Okay. Then, so again from this diagram you can get the same formula like this. So 1 by factor of safety equal to like this. So machine parts are subjected to fatigue loading. So fatigue stress concentration must be applied to only variable stress. Here this is the variable stress. For this variable stress, we multiply the fatigue stress concentration. The equation is taken as like this. Then the other criteria is Goodman criteria. So this is almost similar to the Soderberg criteria. Only thing is here we are taking the ultimate strength. Okay? So according to Goodman criteria, the failure stress line connects endurance limit and the ultimate strength. This the Goodman line connects the endurance limit and ultimate strength of the material. It can be used for any type of material. So that is brittle and ductile. Brittle or ductile. Sorry. So brittle or ductile. However, for brittle materials, the stress concentration factor is applied to both mean stress, that is KT, and for variable stress we take KF. And the derivation is also same as this. Only thing is, so in the Goodman criteria, we are connecting the straight line with sigma E and sigma ultimate value. Same, we are applying the factor of safety to these two values, and we draw the safe stress line. By taking the similar triangles like this, we can get the solution. We can get the Goodman criteria's equation. So from this we get a similar equation, sigma y by sigma ultimate, sigma v by sigma endurance. Now here we are considering the modifying factors. That is, so generally here we consider A, B or C. So A is nothing but the load factor, and B nothing but size factor, and C nothing but surface finish factor. So like this, we consider the various modifying factors for our design. Okay, like this. Here clearly mentioned, for static stresses we are using theoretical stress concentration. For variable loads we are applying the fatigue stress concentration, and we are applying the modifying factors for that. Right. Last one is Gerber parabola. With this parabola, we can find out the factor of safety or diameter of the shaft. So previously we have taken failure points is taken as a straight line, but generally the failure points are falls closer to the parabola. So that's why the Gerber proposed this parabola. So parabolic equation is Sn by sigma mean equal 0 equal to 1 minus sigma m by S ultimate whole square. So this is regarding the procedure.